Welcome to The Explainer. Today, we're diving deep into the cellular world, on a bit of a mission, really. We're going to uncover how a simple cream can act like a master saboteur, tricking skin cancer cells into basically destroying themselves from the inside out. So how in the world does that actually work? We're talking about a drug called fluorouracil, or just 5FU for short. And honestly, it's a fascinating story of molecular deception, where a drug pretends to be a friendly building block, gets invited inside the cancer cell, and then just tears the entire operation down from within. You see, at its very core, 5FU is what's known as a direct cytotoxic antimetabolite. Now, this is a really crucial distinction to make. It doesn't rally the body's immune system to launch an attack. No, it goes in and directly kills the cancer cell itself. Think of it as a targeted strike, not a call for backup. So how does this whole cellular invasion even begin? Well, here's the clever part. 5FU doesn't start out as a weapon. It's actually what we call a prodrug, which means it's totally inactive when it first gets into the cell. It's like a sleeper agent that has to be activated by the enemy's own machinery. Okay, so it really boils down to a pretty simple three-step process. First, the cream gets the 5FU through the door of that rogue skin cell. Step 2, once it's inside, the cancer cell's own internal machinery unwittingly activates it, converting it into its weaponized forms. We call them metabolites. And finally, these metabolites get to work. Now, there are a few of them, but one in particular is the real hero of our story. So here we can see the different missions for each of these activated agents. And while they all definitely cause some trouble, the main anti-cancer effect, the real knockout punch, comes from one in particular, FDUMP. Its mission is incredibly precise and absolutely devastating: to stop DNA synthesis dead in its tracks. So how exactly does FODDUMP pull off this primary mission? Well, to really understand the sabotage, we've got to first take a quick look at the normal process that it's designed to attack. Okay, so in any healthy dividing cell, there's an enzyme called thymidylate synthase. Think of it like a critical worker on an assembly line. Its job is to convert one molecule, DUMP, into another, DMTP, which is an absolutely essential building block for making new DNA. But then, FDUMP comes along and just completely jams the machine. It doesn't just block it, it irreversibly binds to the enzyme, permanently shutting down the entire production line. And this, as you can imagine, leads to this cascading failure inside the cell. Without that key building block, DTMP+, the cell is suddenly starved of a critical component called thymidine. DNA synthesis just stops. It grinds to a halt, and the whole structure for copying DNA, the replication fork, it just collapses. So, the really crucial point here is that this specific targeted mechanism of starving the cell of thymidine leads to a state known in the field by a pretty dramatic name, thyminless death. The cancer cell is literally starved of a key nutrient it desperately needs to replicate, and it dies. Simple as that. But, okay, this brings up a really important question. If 5FU is so good at stopping cells from dividing, why doesn't it just harm all of our skin cells? How does it focus its attack mainly on the cancer? Well, the answer is all about timing. See, 5FU is what we call S-phase specific. This just means it only affects cells when they're in the S phase of their life cycle, which is the specific stage when they are actively making new DNA so they can divide. And right there, that is the cancer cell's fatal flaw. Superficial skin cancer cells are defined by one thing: out-of-control rapid division. They are just constantly in this vulnerable S phase, always cranking out new DNA, and because of that, they are hugely dependent on that thymidine production line. This makes them the perfect, highly vulnerable targets for 5FU's attack, while most of our normal, slower dividing skin cells are left alone. This whole idea of a direct targeted kill becomes even clearer when we put 5FU side by side with another common topical treatment for skin cancer, a drug called imiquimod. You see, they both get to the same goal, but they use fundamentally different strategies. This chart lays out the contrast just perfectly. You've got 5FU, which we know is the direct cytotoxic agent, the saboteur targeting DNA, and then you have imiquimod, which is an immune modulator. It doesn't kill the cancer cell itself at all. Instead, it basically sends out a distress signal, rallying the body's own immune cells to come in and do the job. And here's a key difference. With imiquimod, the inflammation you see is part of the mechanism. With 5FU, the inflammation is just the consequence of the damage. It's the fallout from that direct attack. All right, so after our little tour of the cellular battlefield, what's the single most important thing to take away from all of this? What's the bottom line?
Okay, so the slide gives you the full professor level scientific summary, but let's just break that down into plain English. In simple terms, 5FU kills skin cancer by tricking the fast growing cancer cells into letting it inside. Then, once it's in, it permanently shuts down their DNA production line, which causes them to self destruct. It's a direct, targeted act of cellular sabotage. And that leaves us with a really fascinating question for the future of treatment, doesn't it? Is it better to develop more and more sophisticated saboteurs like 5FU that kill cancer cells directly? Or should we focus more on getting better at calling for backup, rallying our own internal security, the immune system, to do the job for us? The answer is probably going to shape the next generation of cancer therapies.